For this next question, this is problem number 10 on the worksheet. We're given the equations of 4 different surfaces, and our ultimate job is to sketch their graphs in R3. Okay, now I'm going to break this problem up into a few videos, and in this video we'll outline the main ideas and then sketch the graph of this first surface. Okay, I encourage you to then try to complete the graphs of the remaining surfaces before watching the other videos. Is a good way to check your answers and fill in any gaps. Alright, so for this first surface, the equation is z is equal to x squared plus 2y squared. This is what's known as an elliptic paraboloid for reasons that I'll explain a little bit later on. And for part A, it says to find equations for what are known as the yz traces of the surface. Okay, so this is where x is equal to a constant. So what we're going to do here instead is to set x equal to a constant, and I'll call that constant c. So we set x equal to c in the surface equation, and that gives us the equation z is equal to c squared plus 2y squared. Okay, so you see that this gives us a family of parabolas. So if c is 0, okay, we get the equation z is equal to 2y squared, so that's this parabola right here. If c is equal to either plus or minus 1, because of that square on the c, we get the equation z is equal to 1 plus 2y squared, so that's this parabola right here. And if c is equal to plus or minus 2, again, because of that square on the c, we get z is equal to 4 plus 2y squared, so on and so forth. Okay, so what we're calling the yz traces of the surface, these are a bunch of parabolas, right? This c squared term is acting as a vertical shift, right? Where you can think of the scenario where c is 0, right? That's the z equals 2y squared parabola. That's like our base parabola. Cool. All right. So then for part B, the xz traces, well here y is constant. So in a similar fashion, we'll set y equal to c in the surface equation. That gives us the equation z is equal to x squared plus 2c squared. All right. So if c is 0 here, we get the equation z is equal to x squared. Okay, and notice this parabola is going to be a little wider than the parabolas we're seeing in part A. Okay, and that's because in part A, right, there's this 2 in front of the y squared, and that gives rise to that vertical stretch. Okay, so the parabolas in green here are going to open a little wider than what you see in red from part A. And again, this 2c squared term, that's just going to act as a vertical shift, where z is equal to x squared can be thought of as like our base parabola, right? That happens when c is 0. Great. How about C? Find equations for the xz traces. Okay, that's where we set z equal to a constant. So if I set z equal to c in the surface equation, I get the equation c is equal to x squared plus 2y squared. Now notice that this expression on the right-hand side is non-negative for all values of x and y. Okay, and that's because it's the sum of two square terms, right? And so we point that out. C is always greater than or equal to 0. And now, is c ever equal to 0? Well, it is, and that happens at just one point. It happens when both x and y are equal to 0. Okay, so the xy trace when z, which is equal to c, is equal to 0, that, right, is just the single point when we're at the origin here. Okay, now if c is any other positive value, I can go ahead and divide both sides of this equation by c and do a little rearranging, and I recognize, oh, I have the equation of an ellipse. Okay, so I get x over the root of c, quantity squared, plus y over the root of c over 2, quantity squared. Notice that c over 2 comes from the fact that there's a 2 in front of the y squared there. And then this sum is equal to 1, right? And so this is the standard form of the ellipse centered at the origin with semi-major axis, root c, and semi-minor axis, root c over 2. Okay, so you can see here that these ellipses are wider along the x-axis than they are on the y-axis. And so these are our xy traces. Okay, so now what we want to do for part D is to sketch the surface in R3. And we want to do this using these traces that we've described in parts A through C. Now the idea here with the traces is that these traces really are cross sections of our surface. So if I go back to part A, okay, if I set x equal to a constant, I'm really describing a plane. So for example, if I set x equal to 0, I'm really describing the YZ plane. So the YZ trace when C is 0, which again is this parabola z is equal to 2y squared, that's describing the cross section, or in other words, the intersection of our surface with the YZ plane. Okay, so I'm going to go ahead and put that in here. So there's that parabola in the YZ plane when C is 0. All right, likewise for the XZ traces, right? Well, if I set y equal to a constant, right, that is a plane parallel to the XZ plane. So let's say I set y equal to 0. So I'm looking in the XZ plane itself. Well, I know I get the parabola z is equal to x squared. Okay, so that's right there. And now how about for the xy traces? Okay, well if I set z equal to a constant, that's describing a plane parallel to the xy plane. So these ellipses, right, those are the intersections of our surface with all of these various planes running parallel to the xy plane. So here's a whole bunch of those, right? So as I let the value of C increase, right, for my xy traces, right, I'm going to get this growing family of concentric ellipses. So I get, in essence, a parabolic bowl, right, and the cross sections here are ellipses, right? The cross sections parallel to the xy plane, hence the name elliptic paraboloid. All right, now I want to fill this out in a little more detail over here before finishing. So I have the elliptic paraboloid here in green, okay, and if I set x equal to a constant, again this is just describing a plane parallel to the YZ plane, okay, so if I let x vary, I can see, oh, there's that family of parabolas that I was describing in part A. There's the parabola right when C is equal to 0, that's z is equal to 2y squared in the YZ plane. And then as I let x vary, right, I'm going to get a whole bunch of vertical shifts. Also notice the symmetry there. So if x is, say, 2 versus negative 2, right, I get that same YZ trace. And that's just coming from the symmetry of the surface. Okay, likewise, if I set y equal to a constant, just turn around, okay, I get a whole bunch of parabolas again, and notice these parabolas open a little wider than the parabolas I looked at in part A, which we've already noted, right? That's because these are of the form z equals x squared plus some kind of constant, right, depending on what you set y equal to. All right, so those are those cross sections, and then for the xy traces, okay, so this is where we set z equal to a constant, and so that's giving us, right, the intersection of our surface with a bunch of planes parallel to the xy plane. And there's that family of ellipses, and notice, right, these ellipses, there's the x-axis right here, they open wider along the x-axis, right? The semi-major axis is along the x-axis, whereas the semi-minor axis is along the y-axis. Okay, so you put all of those together and you get this elliptic paraboloid, right? So that's going to do it for this video. Again, we'll go ahead and do the other surfaces in the remaining videos, and I encourage you to try to do as many of them as you can before checking your answers in the videos. All right, great. Thanks so much.